Hi everyone, it's Mr. H here for Hamilton Math. This video we're going to look at how to solve three-dimensional trig problems. We're going to do that with triangles that are 90 degrees and triangles that are non-90 degrees. We're going to look at these two situations from the diagrams in front of us, and we're going to look at also how to draw the diagram there on the right. So we're going to begin by recognizing that there's a number of different strategies we need to use. We could use trigonometric ratios, Pythagorean relationships, sine law, cosine law, or the idea of angle of depression and angle of inclination. And so let's look at what each of those are really briefly. This is a bit of review if you've been with me for other lessons, but we have sine, cos, and tan. Those are the trig ratios. Sine is if we have a triangle that's a right triangle, only works for a 90-degree triangle. And if this is the angle here that we're trying to find, that means it's the opposite side, this is the adjacent side, and this is the hypotenuse. And so sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. And the tan ratio is the opposite over the adjacent. So that's for 90-degree triangles. The other thing we can do for 90-degree triangles, and this applies and is always true, the hypotenuse is equal to, when it's squared, is equal to the sum of the other two sides, each squared as well. So c squared equals a squared plus b squared. And so this is the relationship for lengths, and then this is the relationship over here for lengths, but that also works for angles. So most of the time we'll use trig ratios, but there could be situations where Pythagorean relationships are also helpful. Well, what happens if we have triangles that are non-90 degree? We have the sine law, in that case. The sine law says that if we have a side length a over sine a is side length b over sine b, which is side length c over sine of angle c. And so what that looks like, for example, is if I have triangle ABC and it's not a 90-degree triangle, this would work if it was 90 degrees, but let's suppose we don't know that there's a 90-degree angle anywhere in the triangle. Then if I know the angle B, and I know the angle A, and I know side A, but I don't know B, then what I can do is I can use this proportion right here, because I would know A, I would know angle A, I'd know angle B, I'd be solving for side B. But that would also work if I didn't know the angle. So if I didn't know the angle B, but I knew what A, B, and angle A are, then I could just use the reciprocal of that. In other words, I would have sine A over side A is sine B over side B, and I could solve for B by rearranging that, cross multiplying to get B sine A over A. And then I'd have sine of B on the right side, and I'd get rid of the sine by taking the sine inverse of the other side. So that's how I'd rearrange for angle B. So that could be used to find an angle, and it could be used to find a length if we know one pair and then one thing in the other pair. In this case, I knew either the side length in the pair of angle B and side B, or I know the angle in the pair of angle B and side B. The cosine law is this: c squared equals a squared plus b squared minus 2ab cosine c. And that would be used in a few different situations. The first thing is if we know a side. Again, I'm going to just go ahead and I'm going to say this is side C that I don't know. And I know this side here and this side here. I know those are A and B. I know values for that. And then this would be the angle C. Notice here that the angle is always opposite the side that it is opposite from. And so if I know angle C, I know side A and B, then what I can do is I can solve for the length of C by substituting all the values into that equation. So that is when a triangle is giving you side, angle, side. There's no pairs of angle and side that we know, but we have two sides with the angle that we know between them. The other situation that we can use for cosine law is if we have a situation where we know all the sides, A, B, and C. And then we could solve for any of the angles. Let's suppose that we were solving for angle C. And so what we would do is we would rearrange this. We would do that by using the order of operations in reverse. We'd start by doing the subtracting and or adding. So that would be subtracting a squared and b squared. and then we'd be left with negative 2ab cosine of c. Then we keep working through the order of operations in reverse, which I'll just write down here so you have that reference. SAMDEB. So we've subtracted or added. That's how we rearrange equations. We use the order of operations, BEDMAS, in reverse. And now we're moving to the multiplying or dividing. So we're going to divide by negative 2ab. Divide by negative 2ab. And then now that that is down to just cosine of c, I can take the cosine inverse of that, c squared minus a squared minus b squared, all over negative 2ab. And so that is how we solve angle C. The last thing to note here is just the angles of inclination and of depression. And so what that looks like is this. If you have an angle of depression, it's always measured from the horizontal and down. People will often draw something that looks like this, and they will label it here, but that is wrong. That's not where it's labeled. The angle of depression is labeled right from the horizontal down. So remember, for the angle of depression and for the angle of inclination, it is from the horizontal. That's the key. So it's measured from the horizontal. And so what we could do is we could say we've got parallel lines, and so the angle that is here is equal to the angle that's right in there because of the Z pattern that's formed. Angle of inclination is the angle up from a horizontal. So if here's my horizontal line, the angle of inclination is that. So again, if I wanted to make a triangle here, I could say that this angle here is the same because those are parallel lines. The angle of inclination, though, is technically right there. So there you go. That's how you find all those things, and we're going to have to combine those in the questions we're about to solve. So here's our first question. It says Manny is standing at point B, and Joe is standing at point D. They measure the distance between the two of them and the angles shown. Find the height of triangle ABC, which is the height of the cliff that they are standing in front of. So what we have here is we have a vertical triangle. This is the vertical triangle ABC. And then that's probably being measured with some type of clinometer device to measure this angle right here of 38 degrees. And then we have this horizontal triangle that's down on the river. Now, the reason that you might use this horizontal triangle is because this is a crocodile-infested water that you can't measure the distance across the river. So the measurements they've taken are with some type of device that was able to figure out this horizontal angle of 63 and 42 degrees respectively. Now, remember that D is where Joe is standing, and then we have Manny standing over here. And so how high is the cliff? Well, first thing to note is that we have a 90-degree vertical triangle, so we're going to be able to use SOHCAHTOA or Pythagorean theorem for that. And then for the horizontal triangle, there's no 90-degree angle. So we're going to have to either use the sine law or the cosine law. So here's how I'm going to make a plan for these. You may see the way to go about these, but this plan I'm going to show you is going to work every single time. I could find something if I knew something else. I could find if I knew. And so the first thing we're going to say is I could find the height. Well, I could find the height if I knew the length of BC. Because if I knew the length of BC, what I could do is I could use the tan ratio. Because tan of 38 degrees is going to be the opposite, which is the height, over the adjacent, which is the length of BC. So that's what I could use. Well, how could I find the length of BC? So now what is over there, we're going to put in the I could find. We're going to say, well, how could I find that? So I could find the length of BC if I knew angle BCD. I could find the length of BC down here if I knew BCD, the angle right in here. And the reason for that is because once I know this angle here, I have a pair of angle and length that I can match with another angle and length that I can solve. You might think, well, I only have kind of one thing in that pair and one thing in the other pair, but I know two angles already in this triangle, don't I? I know the 63-degree angle and I know the 42-degree angle. So angle BCD, I can solve that fairly simply. Angle BCD is going to be the other two subtracted from 180. Because always in a triangle, the three angles add to 180 degrees. So there's step one, there's step two, and there's step three. This is how the I could find if I knew works. We work backwards from what we're trying to find at the beginning, and then we build our steps backwards according to that so that we're working forwards through the problem. So the first step is to try to find angle BCD. Angle BCD is 180 minus angle CDB minus angle CBD. And so it's the 42-degree angle and the 63-degree angle. And so when we subtract that, we get an angle of 75 degrees. And so now we can use that for the next step. So step number 2, we're trying to find the length of BC. BC is in the triangle, the horizontal triangle. If we label this, I'm labeling that length D there, okay? And so BC is going to be equal and equivalent to length of D. So what I'm going to do is I'm going to use the sine law. I'm going to say D over sine of angle D. And then what's the other pair I know? Well, the other pair I now know this is 75 degrees. So I know the length of C, which is 68.5. And I know the angle C, which is 75 degrees. So I'm going to be able to go ahead and sub these in. So D over sine of 42 degrees is going to be equal to C, which is 68.5, over sine of 75 degrees. And I cross multiply here to get the sine 42 up. So I go say that D is 68.5 times sine of 42. Make sure it's in degrees when you put in your calculator. We divide that by sine of 75, and we find the length of D to be 47.45 meters. Now, one thing that's important is if we're rounding the final answer to the nearest meter or something like that, it didn't tell us how to round it, but most of these values have 2 significant digits. Then we want to take at least 2 more decimal places than what we're trying to round the final answer to. So because I'm trying to round the final answer to the nearest meter, I'm going to just take 2 more decimal places to eliminate that rounding error. So now we're on the last step, and step number 3 is now finding the height. And so as we said already, that is tan of 38 degrees. Tan of 38 degrees is the opposite, which is the height, over the length of BC. And we know the length of BC, we just solved that. So we can say that the length of BC, which is 47.45, just cross multiplying with the BC. So I'm bringing that up. So 47.45 meters times tan of 38 gives me a height, and that height of the cliff is 37 meters. And so we can conclude, therefore, the cliff height is 37 meters. So that's how you do that first 3D problem. Which brings us to question 2, which is probably the most difficult one because it usually is not provided with a diagram. And I'm going to show you how to actually draw the diagram, and then we're going to go ahead and solve it from there. So let's read the question first. It says, someone in a hot air balloon at an altitude of 226 meters observes the angles of depression of one point on the ground as 2 degrees and of another point as 3 degrees. The horizontal angle between the lines of sight to the 2 points is 80 degrees. What is the distance between the 2 points? So let's deal with this one piece at a time. So we are up somewhere at an altitude of 226 meters. So that means that above the ground, we're 226 meters above the ground. So let's say this is a side view. If we are looking at the angles of depression to one point on the ground as 2 degrees, that means we're going to look down and we're going to see an angle of depression of 2 degrees. Now this is clearly not a 2-degree angle, but that would mean the angle of depression is the angle in here, which is 2 degrees. I'm going to call this point that we're looking down to as point A. And then because this is an altitude, a height above the ground, that means this forms a 90-degree triangle. I'm assuming the ground is level and the height is always a vertical height. So that means that within this 90-degree triangle, we know this angle here is 2 degrees. Now, I'm going to look at the other triangles separately first for the 3-degree one now. We're going to have an altitude of 226 meters. And then we are going to look down with an angle of 3 degrees, angle of depression. So that's going to be this angle here is 3 degrees. And then for the same reason as before, that's a 90-degree triangle, which means this angle here in that 90-degree triangle is 3 degrees. Again, a side view. So these are both side views looking at these 2 points. One looking down to point A on the left and the one looking down to point B on the right. Now, the mistake that people make is then they just stick these two together and say, well, doesn't that just mean I could just add this length to this length and figure out the length from A to B? Well, it's not that simple because of the last statement. So the last statement says this. It says the horizontal angle between the lines of sight to the 2 points is 80 degrees. So what that means is if we shift to a top view, what we're going to see from a top view is we're going to see that if I look at the lines of sight to the 2 points is 80 degrees. So the lines of sight, so in other words, if you look out to this one here, point A, that's one line of sight. The other line of sight is looking out here to point B. The horizontal angle between those is 80 degrees. So that's a top view. So what we have to do now is we have to somehow put together these three triangles. We've got these two vertical triangles. These are vertical. And then we have this horizontal triangle that connects them. And so if we label this point down here as point C, then hopefully you can start piecing things together and realize, well, point C is at the bottom of the, or it's the bottom of the altitude, directly below the hot air balloon. So point C is those 3 points on those three different triangles. So when you bring all those together, it's going to look like the following diagram. So there you go. We've got the two vertical triangles there. This is designed to look like a 3D object. So the ACD and BCD, those are vertical triangles. And then we have got triangle ABC, which is a horizontal triangle. So now what we're going to do is we're going to solve that. I'm going to get rid of the other two-dimensional drawings that I did and just work from the 3D drawing. So just like before, I'm going to say I could find and if I knew. I could find if I knew. So the first thing we want to identify here is that what we're trying to actually solve. We're trying to find the distance from A to B. So that's length AB. So I could find the length AB if I knew a couple of things here, right? If I know the angle that's opposite it, but if I know the side A to C and I know the side of B to C. So if I knew AC and BC, because then I would know side, angle, side, and we'd be giving SAS, and so we can use the cosine law to solve that. So let's talk about how we're going to solve AC. Well, I could solve AC if I knew, well, I have enough to know it, right? I need to know, because it's a right triangle, I need to know the angle, and I need to know a side length. So I know the angle, I know the height, so I could use the tan ratio, or the tangent ratio. And I can do the same for side length BC. If I know the angle, which I know it's 3 degrees over there, and I know the height, which I know is 226 meters, again, I can use the tan ratio. So again, I'm going to label my steps as 1, 2, 3, working forwards through the problem to get to the final result I'm looking for, and I'm going to carry out those steps. So step number 1, I know that tan of theta, I'm just going to write out the general form here quickly first, but it's opposite over adjacent. So tan of the 2 degree angle is going to be equal to 226 meters. That's the opposite, the height. And the adjacent side to the 2 degree angle is length AC. And so now what I'm going to do is I'm going to multiply both sides by AC and divide both sides by tan of 2 degrees. So what ends up happening is the AC and the tan of 2 degrees end up switching places. And so I'm going to get AC equals 226 divided by tan of 2 degrees. And the answer I get for that is I end up finding a length of 6,471.8 meters. Again, I'm trying to keep some extra decimal places here so that I'm more accurate. The more decimal places you keep in your calculator, the better. So I'm going to do the same thing now for the 3 degree angle. And so that's 226 over the length of BC. And I get BC again by multiplying both sides by BC and dividing both sides by tan of 3. Switching those up, I get 226 over tan of 3 degrees. And the length that I get there, because it's a bigger angle, it should be a little bit less of a length on the bottom. So it ends up being 4,312.3 meters. So now I've carried out steps 1 and 2. The last thing to do now is to solve the length of AB. And so that means we're going to use the cosine law. I'm just going to change the color here so I can label a few more things on the diagram and you can see exactly what I'm labeling. The first thing to note is that BC, the length of BC, is what I'm going to call length A. So that's going to be the same as length A. So I'm going to relabel that according to the vertices on the horizontal triangle. The other thing is that AC is going to be relabeled as B. So I'm going to label this B as this value. And then the length of AB is that C side that corresponds with the angle that's opposite it, angle C. So I can write this out as C squared equals A squared plus B squared minus 2AB cosine of angle C. So C is equal to the square root of A squared. Well, A was 4312.3. We're going to square that. Plus 6,471.8 squared minus 2 times those same numbers again. Sometimes you have to extend your square root to make everything fit. 6471.8. And then cosine of angle 80 degrees. And when you've done that, assuming you've done everything properly, the key to remember with the cosine law is to make sure that you don't subtract the 2 times the numbers until you first multiplied it by cosine of 80 as well. But you should end up with a C value of 7,127 meters. Maybe slightly different depending on rounding error. And so what we could say is therefore points A and B are 7,127 meters apart. Now you might think that looks a long way. Remember that the diagram is not to scale, right? The 2 degree and 3 degree angles are very, very, very small. So really this is a very, very stretched out diagram. And so this is actually quite accurate compared to what the numbers that were given are. So there you go. Please, if you like this, like and subscribe. Welcome that, and stay tuned for the next video.